Hello, seniors. Mr. Reynolds here with you, talking today a little bit about wave functions. Let me explain a little bit about this week and about some of the assignments. We were originally only going to have one class meeting this week. That's going to be on Thursday, and the eighth period class would have met twice, but one of those we go over some worksheets and whatever. So what I've decided to do is, instead of having you cover two related but sort of separate topics all at once, we're going to break it up a little bit and have you cover some wave functions first, and then we're going to talk about Heisenberg uncertainty principle, looking at uncertainties and momentum, position, and all that second. Okay, so that lesson will come out probably on Wednesday. Today's a little bit about wave functions. It's really not too bad, but we are going to sort of get into a few other little topics with wave functions, but really this one should be pretty quite short. So the basic idea of wave function is this. If you have let's say you have a container here, and you need to know where your little object is. You want to know where the little red X is. I want everybody right now to point to where the little red X is. I want your finger on the screen. That's right, you too. Okay. So that's where the little red X is, exactly. And if we treat things like particles, it's very easy to identify where an object is. Hey, it's right there in the top right-hand corner of my little box, no problem. For most things we deal with in the macro world, that's fine, okay? For example, right now I can pretty much guess our positions. You're probably at home doing your social distancing, or as Mr. Reynolds likes to call it, heaven. Wave functions, particles behave in fairly normal ways, which we would understand. However, this is not the normal stuff we understand chapter. This is the quantum chapter. And in this chapter, we're looking at smaller things. We're looking at things such as electrons. And we know that electrons, just like everything else, but mainly electrons, can behave like particles sometimes, and they can sometimes behave like waves. And so if I was to show you the same box and ask you where the electron is inside the box, that's not really a question scientists can really answer at all. It turns out that if we were to answer that question, it would sort of mess up where the object was, and all of a sudden we wouldn't know where it is anymore. And so we never talk about the position of an electron with certainty. We never talk about the position of an electron as in, oh, that electron is at a radius of this many meters. Now, we did that with the Bohr model of hydrogen because hydrogen is sort of simple and we can make some approximations. But with most electrons, it gets a lot more complicated. Thankfully, we are going to try to keep things simple. We're going to keep things simple today because electrons can move anywhere in 3 dimensions. We are going to restrict an electron to simply 1 dimension. We're just going to think about an electron as it exists on a plane, and we're just going to look at a line. And we're going to imagine that the electron has to be somewhere between position A on the left and position B on the right. In fact, what we'll do is we'll have what we call infinite potential walls, which mean in order for the electron to get out of the bottom of this hole, perhaps, it would need an infinite amount of energy to escape. So it's never going to escape. Sorry, I had a cough there. Wink, wink. You can't see me winking right now, but I am winking because it sort of can't escape. We'll get to that later. So the electron has to be somewhere between A and B. Now, the tool we use to understand where the electron might be is called the wave function. Now, the wave function is a mathematical function. It's a line on a graph that can be used to understand the probability of where an object is at a specific time. Now, often the wave function will be used maybe to look at where an electron is in relation to a proton. Maybe the wave function is used to simply understand the wave nature of the electron itself. Okay, and so what we're going to do is we're going to look between A and B, and we're going to look at the wave function. Now, the symbol for wave function is a psi. And the way I can remember that's a psi is because I was a big Ninja Turtles fan growing up. Now, some of you may remember the Ninja Turtles. Some of you maybe horrible and don't. But Raphael, one of the lamest of the Ninja Turtles, he's the guy that liked eating pizza a lot, I think. No, that was Michelangelo. Now, Raphael's just the lame one. But he used a psi, and it was a 3-bladed poking device he used to defeat Shredder and his minions and Dr. Brain and all these kinds of things. Anyway, the wave function is a psi. And the equation we're going to use, I say we're going to use it, we're not actually really going to use this equation, but it is in the data booklet. In topic 12.1, we see an equation that says this. PR equals the absolute value of psi squared times delta V. Let me explain what this equation means, okay? What this equation essentially means is the probability of finding an electron in a specific area is proportional to the square of the wave function. So again, wave function. We're going to draw a mathematical shape, a graph, on a line on a graph, and the square of that value, the square of that amplitude, is going to be the probability of finding the electron. So for example, and again, remember we're only looking in one dimension right now. We are not going to 2 dimensions, we're not going to 3 dimensions. It does get hideously complicated after this point. So if I draw a line right here, beautiful purple line, I'm going to draw a simple wave function. So I'm going to draw a wave function that looks like this. Okay. Actually, well, tell you what, I'm going to draw a wave function like this. Okay. Now, the electron can exist anywhere from A to B. What I want you to do is I want you to think about this wave function here, and I want you to think, where would the electron most likely be found? Where would the electron most likely be found? Have a think about that real quick. Hopefully you're pointing out up here. The electrons we found somewhere in this area. The reason I say that is because the square of this wave function this is obviously the highest amplitude wave function, and so I'm more likely to find the electron in this area right here. What about down here? Would I be negatively likely to find the wave function, or what's going on with that? Well, the answer is I would be able to find the electron at this position. It's sort of maybe a medium probability. And the reason is that in order to find the probability, I've got to square the wave function. So all the negative values will flip up and become positive. So nothing we need to worry about there. Now at positions, let's call it X and Y and Z. Those are places where I'm not going to be finding the electron. Those are places where the probability of finding the electron is 0 because the wave function at that point is 0. And so you can draw wave functions and understand sort of what they mean. Really, they just tell us the probability of finding an electron at a certain point. Now, we are going to be using this idea next chapter or next topic when we start looking at uncertainties and things like that. But for now, that basic understanding of a wave function will be helpful. Now, there's one other thing we can do with wave functions, and that is, again, well, I say one other. There's 2 other things, really. But imagining we have a wave function, and sometimes we have a wave function like the one you see here. This wave function may be due to some other aspects. Maybe there's other electrons floating around. Maybe there's a proton somewhere. There's different forces acting on that electron. I don't know why the electron is more likely to be here than it will be anywhere else. I don't know why that is, because who knows what else is going on, but that's what's going on. But let's imagine an electron experiencing social distancing. You may know what social distancing is from what I can tell from some of my interactions with you all. You're about to bounce off the walls already. I understand. So let's imagine an electron that's just hanging out by itself. An electron that doesn't have any forces on it. There's nothing else causing it to be going anywhere else or anything like that. Well, in that situation, our electron actually forms what we call a standing wave. The electron is going to be within this area. Again, this is an area of infinite potential walls. Sometimes we call this an electron in a box, where the electron can't get out of the box. And so what we'll find is a wave function that will form a standing wave. Okay, so maybe a wave function looks something like this. Sort of a standing wave kind of situation where we have a node on both sides of the standing wave. And so here, again, I'd be more likely to find the electron in these two spaces. I would have 0 probability of finding the electron in the middle. But one sort of neat thing we can do is we can take a look at, what's the wavelength of the electron? Let's imagine the length. This whole thing is L. That's the width of the box, perhaps. In this case, the wavelength would equal L, and I can use my de Broglie wavelength equation. I can say de Broglie wavelength equals h over p, and maybe I could find the momentum of that electron. Maybe I could go further and say, kinetic energy is p squared over 2m, and I could plug that in, and maybe I could find the energy. So that would be h over square root of 2m ek. And so this wave would have a certain amount of kinetic energy. And then maybe I would take that electron, give it some more energy, and maybe it's going to form a new standing wave. It's going to form this orange standing wave. Well, the wavelength has gone down in that situation. If the wavelength has gone down, that electron now has some more energy. And that's stuff that we can calculate. If we had numbers to this, we could calculate all these things. And that's something we will be doing once we get that second part of this chapter. So again, an electron sitting by itself in an empty box with no other forces will tend to form a wave function. And again, this is our wave function that has a bit of a standing wave to it. And we can, again, use that with a de Broglie wavelength to find out stuff about the electron. Sort of neat thing. One last little topic, and I find this topic sort of interesting. I find all this stuff pretty interesting. It's mind-blowing. Okay, brain sort of hurts to think about it, but guys, you are smart enough to understand this. I'm going to show you a video after this video. It's from Khan Academy, and it gets a little confusing at parts, but I think you can follow. And I think you can sort of see how Schrodinger and some people came up with this idea and did some things. And it's really cool that we're able to cover this in high school. Even though we're doing distance learning now and stuff, you're learning serious things that I never learned in college. And so whether you're going to be a physics major or not, you're going to be pretty well off. Let's see. So we're going to talk about, again, infinite potential. So this is our box where the electron has to stay somewhere inside of this box. And we see there's a wave function going on. And I'll just draw a little standing wave here. Maybe here's our little electron standing wave. But what we find, the wave function is actually a function. And most math functions don't have a very specific, strong end to them. In fact, if we really zoom in, you would think that the probability of finding the electron outside these walls is 0, because it does require an infinite amount of energy for that electron to exist outside this box. However, it's not. What we find is this wave does not go quietly into the night, as Michael Caine would say in Interstellar. In fact, the wave function just gets slightly smaller, and there's a very small but very measurable amount of electrons that can actually exist outside an impenetrable barrier. Again, the wall of this container requires infinite amount of energy to pass. Yet in quantum physics, using wave functions, we can see that there are going to be some electrons slightly outside of it. Let me give you an example of where this is actually used in the real world. If we want to measure the shape and contours of really small things, what we do is we get a perfectly sharp needle, almost as perfectly sharp as we possibly can. And we get it close enough to an object that's bumpy on an atomic scale. I mean, it's incredible. We're very, very skinny, thin, very close, very small tolerances here. And as we get this needle close enough, the electrons tend to jump across this area of infinite potential energy. And they tend to jump from the needle into the material being measured. We call this quantum tunneling. And you may hear of a scanning tunneling microscope or a quantum tunneling microscope. Because what they'll do is they will actually measure the amount of electrons that are traveling into the substance. And by knowing how many electrons, by measuring the voltage and current, basically, by measuring the current of electrons traveling through, they can figure out how far away the little needle is from the surface. And they can map things to a level and precision so far beyond the scope of the visible wavelength of light. It's really amazing things that they can do. And they can map atoms, where we could never do that with visible light. But using quantum tunneling, this is what's going on here. Quantum tunneling, where an electron can actually tunnel through an infinite potential. That's wild. That's sort of like how if your parents force you to stay in your house, you may be trying to tunnel out of your house soon. I don't know, to get away from the social distancing, which, guys, you should do. And again, this is a serious thing, and we don't want to make light of it. But hey, if you can use it for metaphor, I'm all for it. So this is wave functions. Again, wave function is a mathematical function that describes the probability of finding an electron in a certain spot. If you recall back to chemistry, you didn't study electrons orbiting around a nucleus. Instead, you studied orbitals. You studied an area where you have a very high probability of finding that electron. A three-dimensional area. Maybe it was shaped like a sphere, maybe like a donut, maybe like an infinity symbol, whatever. But an area where you are likely to find the electron. Those orbitals, those areas, are simply three-dimensional manifestations of these one-dimensional wave functions, right? And at our level, one dimension's fine. But you go 3 dimensions, you do Schrodinger's equation stuff, it gets a little more complicated. So I hope that makes some bit of sense. I'm going to have you watch a video next. This is from Khan Academy. He's going to talk a lot about some of the similar things and some of the historical background behind wave functions. I don't have any problems for you to work on. If anything, finish up some of those worksheets we've been doing. We have a little Google Meet or whatever session where we can go over some stuff. So worksheets and stuff like that. But the problems will really come with the second set of work, which I'll probably put up on Wednesday because I've got to, put it together. But the second set is going to involve the Heisenberg uncertainty principle, and it actually has a good bit to do with wave functions. And so that's why I want to cover wave functions first, but you'll get that then. Guys, I hope you're doing all right with this whole being away from each other. I mean, I know, being away from school is great and all, but I think you're realizing that there are some really nice things about being in school with your friends and stuff like that. Hopefully this whole situation ends quickly and, we can get back to our normal grind. I know, obviously we got the DP test coming up, guys. I'm going to do everything in my power to get you ready for that. And, just keep working, keep pushing. Don't let down in this month away from school. It's not the ideal time to have a month off of school, but hey, it's what we got. So, let me know if there are any, diversions that, you need me to make a video about, because I know some of you are, really suffering without Mr. Reynolds' story time going on right now. So yeah, just give me some feedback on that. We can have some off-topic stuff as well because I'm going to start getting bored here at some point too. So hope you're doing well and talk to you soon.